Hi everybody, welcome to this presentation entitled Improved Solar Module Model for Qspice. This video is a continuation of this previous video, Qspice number 10, Modeling Solar Modules. Here we have the outline of this presentation. We will start with the introduction. We will see how to add the irradiation effect to the solar module model. Then we will see the model implementation in Qspice, an example of use, and along the video, as usual, we will be showing several Qspice simulation results. As usual, thanks go to our industry mecenas, Frenetic. Frenetic is a company dealing with the optimization of power converters using artificial intelligence. You can try their software for free using the link provided in the description of this video. In the previous video, Qspice number 10, we saw how to implement a solar module model in Qspice using the Carmichael-Hanifa model, which is based on 4 electrical parameters. This is the equation of the model. Here we have the characteristics that we saw in this previous video, and here is how to calculate this parameter M from the voltages and the currents that we have from these values in our panel. And with this we have everything to do the implementation as we saw in this previous video. However, in this previous video, we didn't see the effect of the irradiance on the current voltage characteristic of the panel. And this is a very important effect, especially when we want to simulate maximum power point tracking methodologies in Qspice. So this is the goal of our video today. We are going to see how to improve our model. So we are going to incorporate the effect of the irradiance received by the solar module. So this is the panel that we are going to use. Is the same that we saw in previous video. Here we have the characteristics, and then as we can see we have one characteristic for each value of the irradiance on the solar module. So what we want to do is to add the effect of the irradiance into our model, and this will be very useful to simulate maximum power point tracking methodologies. Here we can see a summary of how we are going to do the modeling. The basic model is a current source. This is the expression as we know, and in total we have 4 parameters. We have the short circuit current, the open circuit voltage, and the voltage and current at the maximum power point. And we are going to model these 4 parameters as a function of the irradiance E following a linear relationship, which I think that is quite good for our purpose. And then, as we have seen before, the exponent M can be obtained using this expression. So what we are going to do is to use our image digitizer that we developed in this previous video with Python number 4. Here are the characteristics of the solar module, and these points here correspond to the short circuit current. So using the image digitizer, we get this file with the value of the irradiance and the value of the short circuit current. And now, using this WinPython script, we can plot the different points of the short circuit current as a function of the irradiance, and we can do a linear regression, as we can see here, which is very good because the short circuit current is almost linear with respect to the irradiance, so we get these 2 parameters, and this parameter is almost equal to 0, very small current here, because the short circuit current is directly proportional to the irradiance E. And then we do the same with the other parameters of the model. Here we have the open circuit voltage as a function of the irradiance. So these are the points that we have gotten from the data sheet, and this is the approximation using a linear function. So this is the expression, and here we have the parameters. Same thing with the maximum power point voltage as a function of the irradiance. So we can see that the approximation is quite good, it's less than half volt. So I think that is good for many applications. We could do a better regression, but right now we can be happy with using a linear relationship, and this is for the maximum power point current. In this case, the linear regression is very good because, again, for the maximum power point current, there is a linear relationship with respect to the irradiance. So these are the parameters that we are getting and that we can use in our model. And here we can see the implementation on Qspice. So this is the current source that is going to model the behavior of the solar module. We are using the time as voltage in order to test our model. So here is the time t to generate this voltage, and then we apply the current to a 1 ohm resistor and calculate the power using this multiplier. And these are the parameters of our module to implement the linear regressions. So here we have the calculation of the open circuit voltage. This is the calculation of the short circuit current, the maximum power point voltage, the maximum power point current, and the exponent m. We can see that all this depends on the voltage at the E point, which is this point here, and this is the input for the value of the irradiance. We are going to do a dot step analysis with different values of the irradiance to test our model. So now let's run the simulation and see the curves that we are getting. And here we have the results. On the right, we can see at the top the value of the power of the module as a function of the voltage. We know that time is now voltage, and below we have the current as a function of the voltage. So we can see that everything is going well. So now we can go ahead and implement our model, including the effect of the irradiance. This is the implementation of the model in Qspice. This is the symbol. We have the anode, the cathode, the input for the irradiance. These are the different parameters of our model. Here we have the schematic of the model, and from it we can get the SPICE definition that we are going to embed in our symbol. If you are not familiar with this process, I recommend you to watch these videos, Qspice number 1 and tips and tricks number 3. And here are the results of a simulation using our new component. Now we are applying a voltage source to the solar module in order to go through all the points of the characteristic and then be able to do the plotting using Qspice. And we are doing this for different values of the irradiance. We are using this diode here in series to avoid having negative currents, so we can have a nicer plotting. And here on the right we have the power for the different values of the irradiance, and below we have the current also for the different values of the irradiance, and both of them as a function of the voltage across the panel. And now to do a better testing of our new component, we are going to do a simulation using a power converter. In this case, we are using, as we can see here, a buck converter. Here we have the voltage across the panel. We have used an input capacitor to filter the current, so we are going to have a current circulating through the panel with low ripple. Here we have the output voltage, and we want to obtain the value of the duty cycle at which we are going to have the maximum power in the panel for an irradiance of 1000 watts per square meter. So for this we can say that the input power is approximately equal to the output power. The converter is going to operate in continuous conduction mode, so we can say that the output voltage is the duty cycle times the input voltage. So we have this relationship between the duty cycle, the load of the converter, and the ratio of the input voltage and input current. In our solar module, the maximum power point for an irradiance of 1000 watts per square meter is when we have a voltage of 33 volts and a current of 8.7 amperes. So from this we can get the value of the duty cycle, which is equal to 0.51. And here we have our circuit to test the solar module. This is the buck converter. Here we are using a comparator to generate a PWM signal that we are sending here to the switch to drive the switch, and we are now generating a duty cycle of 0.51. And with these statements here, we are generating the average voltage across the panel, the average current through the panel, and the power delivered by the panel. So now we can run the simulation and see the results. So here we have on the right the voltage across the panel, the current delivered by the panel, this is the output voltage of the converter, and this is the current through the inductor. And on the left we can see the values of the voltage across the panel, the current through the panel, and the power. So we can see that we are operating at the maximum power point of the panel. However, if we, for example, change here and increase to 0.6 and run again the simulation, we can see again the waveforms, and now the voltage across the panel is 25.8 volts, the current is 9.48 amperes, but the power is only 244.9, so it's smaller than in the previous operating point with 0.51 for the duty cycle. And if we go below and select, for example, 0.4 and run again the simulation, we can see that we are also in a point at which the power is again smaller. We are 36.6 amperes and 221 watts, while when we are operating at 0.51 we are getting a power of 288 watts. Well, with this we get to the end of this presentation today. I hope that you find this information useful. Please let me know if you have any comment or question using the comments box of this video. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.